there are computers, there are people who compute, okay, situated at different locations around the globe, and they will pass information from one computer to the next computer, and there's a conductor in the center who would have a red and green light and tell and slow people down or accelerate people when the message is not going the right speed. And those of you who are in computational fluid dynamics immediately know what that's talking about. Okay, we're talking about the CFL criterion without CFL. So what he did, the first numerical weather prediction, is a grid over Europe, and so you predict the pressure, temperature, and wind. Obviously, the temperature changes in temperature changes the density of the air, and changes in the density of the air changes in the pressure, and if you have two places with different pressure, you have the pressure gradient force, and so that changes the wind, etc., etc. So a very simple idea. You know the equations from a long time ago. So, unfortunately, the first prediction was a really bad failure. Okay, the predicted surface temperature trend predicted was 145 millibar per 6 hours, and the real change was much smaller. So since 1922, nothing much happened until 1950. So the first successful numerical weather forecast was done in March 1950, and it was done on the ENIAC computer in the naval testing grounds in Aberdeen, Maryland. The lead was this guy who is my thesis advisor, and so there's several steps that I will talk to you about. One is what they did, obviously. This is a US calculation. It's the grid over the US, and they made several forecasts, 24-hour forecasts and 48-hour forecasts. And it took them 33 days to debug the code. This is one layer over the atmosphere, okay, and to do the forecast. And this is the computer, the ENIAC with fewer than 10 words read-write memory. And so this is a function table, okay, this is the memory here, okay, and these are people who help manage the cards. And so to advance one time step, what is more interesting to me here is that it's a marvelous story that you have punch cards, and to advance each time step, you calculate parameters that you know, okay, the change in you know the Coriolis force, you know where you are, the gravity, the function tables. This is the storage, this is the memory. And then you have ENIAC operations. So these are actually using the 10-word memory. And so you advance, you do the differencing, you do the addition, all the operations are done here. And then it outputs a deck of punch cards. And then you take the punch cards, and then you figure out where the next set of operations are, okay? And then you put it through the 10-word memory. So it takes 16 of these operations to advance one time step, which is 15 minutes. Okay, so this is a story they tell, is that the punch cards would go da-da-da, and they would go a jig, and they would go a dance while the punch cards are, you know, so this is round-the-clock enterprise. But the success of it, came of that operation, that very first numerical weather forecast, came from several things. One is better observations. Second World War, I don't need to tell you, there were lots more meteorological observations. And so then what you have, weather forecasting is an initial value problem. So better observations mean that you have better initial conditions. That, you know, good start. Second is that it was a faster computer. You know, we had the ENIAC, okay? So they could make a 24-hour forecast in 24 hours, so it's nearly catching up to real time, okay? But most important, that's the most important reason for the success is Charney's recognition, and that was his PhD thesis at the University of at UCLA, that the atmospheric flow is quasi-two-dimensional. The radius of the Earth is 6,6375 kilometers. The atmosphere is 10 kilometers. Okay, so to lowest order, it's a two-dimensional fluid, and it's a fast-rotating fluid. And those of you who've gone through that, this is the Taylor-Proudman theorem. Okay, so the flow is quasi-two-dimensional. It's quasi because all the action happens in the vertical. The flow, all the energy, most of the energy is in the horizontal velocities, but the action of getting energy, getting storms, getting rain, getting anything, any energy conversion happens in the vertical. So recognizing that, then you can do approximations to the equations of motion, so then you can do the quasi-geostrophic vorticity equations, or quasi-geostrophic just meaning when it's advection, it is two-dimensional, and then you allow for the vertical motion. The more important thing is to recognize that there are certain waves in the atmosphere that are just nuisance, okay? The correspondence of the time says, who cares about the high notes? Okay, we care about the low, okay? So Richardson's failure in that is that he did not recognize that the gravity waves, you have sound waves in the atmosphere, and so he blew up. For all practical purpose, he needed a very, very small time step, and he blew up. But the other thing is that with the observations, then you solve the equation in pressure, and pressure is a scalar, and so it is much more stable. You know, it's easier to solve than the momentum equation, so they could take much larger time steps. So that was the first success, and after that, there are many. You know, I can't give you the history of atmospheric science, but here are the equations. Okay, momentum equation, mass, conservation of angular momentum, conservation of mass, P equals rho RT, okay? Energy, conservation of energy, so that you have energy, the change in temperature, this horizontal advection, the wind blows, cold air, hot air. So we have all the terms on the right-hand side are the forcing functions. We have changes in energy because the atmosphere absorbs and reflects solar energy. There's a change because we have the greenhouse effect. There's the long wave energy that goes in all directions. We have also sensible heat. Sensible means the heat that can be felt, so think of it as convection in the classical physics sense. So you have a temperature gradient, there is heat transfer, and latent heat. Okay, evaporation of water from the oceans. The ocean supplies latent heat, converts the liquid to vapor. The vapor in the atmosphere, when it condenses, releases the heat to the atmosphere. So the heating, the source of this is three-dimensional. Okay, it varies locally, varies with the composition, varies with the clouds, varies with everything. And obviously now we add in water vapor, conservation of water in the atmosphere, so there's horizontal advection of water, but also in situ evaporation and condensation of water. So all of that we think we sort of know. But the bugaboo comes in here. Okay, what I have put in as convective mixing. So this is, think about it as clouds. I look at clouds. They're poetry. There's lots of poetry about clouds, but I have to write an equation about the clouds. So the clouds, when you see plumes, when you bump around on the plane, okay, I'm thinking about how the cloud is formed. Okay, you have a shearing flow, you have a convective plume and a shearing flow, and the plume is going to entrain stuff, okay? It's going to entrain dry air, and how high it goes depending on the entrainment, and then you can see the cirrus clouds, the detrainment, and in all that clouds, what am I seeing? I'm seeing latent heating, there's condensation, okay, so it's heating the atmosphere, but not only that, it is mixing the momentum in the vertical, it is mixing the temperature, it is mixing the humidity. Okay, so a lot of the story of the climate modeling is in the subgrid scale, it's in turbulent mixing, even though we're looking at the whole climate. In the ocean, we have a similar set of equations. So I put 2 because the ocean is incompressible. So we can look at the momentum equation in the same way, the advection, the Coriolis, pressure gradient, friction. And so then the equation, so conservation of mass and pressure gradient. So in the ocean, we can assume the hydrostatic approximation. Unfortunately for us, the ocean, there is no nice thing, P equals rho RT. Okay, so the equation of state for seawater is a mess of a polynomial that nonlinear. that you have to worry about the temperature, the changes, the distribution of temperature, salinity, the pressure, but also the sodium, the chloride, the everything else. Okay, so the composition of seawater all enter into this polynomial that describes the equation of state. So ocean, unlike the atmosphere, which has internal heat and sources and sinks of heat and water vapor, the ocean is conservative in the interior of the ocean. So there's no internal sources of heat, there's no internal sources of salt or momentum. So everything that happens for the ocean happens at the boundaries. So there's momentum input at the top of the ocean, the wind dragging the ocean. There's vorticity input to the ocean at the top of the atmosphere. And so you have heat input, obviously. And then precipitation is adding salt water, precipitation is adding fresh water, evaporation is removing fresh water. So there's a change in the salinity due to precipitation and evaporation at the top of the atmosphere. The ocean, the challenge is the bathymetry, okay, coastline shelves, and so it is very irregular. So it is a real challenge when we talk about climate models. We do not have a nice bathtub of an ocean. So all the friction, all the dissipation, everything along the irregular coastlines is a real problem here. So when we talk about numerical weather prediction, you're all familiar. You know, I just talked about we have initial value. So we take the observed state of the atmosphere. Now what we do is we have the raw observations, the temperature, the humidity, the pressure, the wind, and everything. Then it goes through a super data large assimilation exercise, and then using either some variation of an ensemble Kalman filter or using 4D variational methods. But anyway, so you have the atmosphere, and so you make predictions of 6 hours, 12 hours, 18 hours, etc. So you all know that the error grows with time. So the initial conditions are not perfect because nobody observes at the middle of my grid box, averaging over the, okay, so you have whatever instantaneous observation, so there is the translation of the instantaneous observation to the state variable of the model. There are portions of the world, for example, over the Southern Ocean, where we have very little observation. Okay, so then you have the initial conditions are not perfect, the models are not perfect, and so the errors would grow in time. And all of you know the limit to forecasts, we don't look past 5 days. Okay, 2 weeks is a bit of a stretch. Okay, so here is the weather forecast. It's an initial value problem. In the last several decades, what we have done is started to look at seasonal climate prediction, El Nino predictions, for example. And there, the models, the equations may look similar to the weather equations, but then we look at the problem in a slightly different way. We don't think about it as sort of an initial condition. So now we have an ensemble of initial conditions. And so then we make an ensemble of forecasts. And the forecasts, even though we are cranking along at 5-minute or 15-minute time steps, we're looking at the statistics. So this is very important. The climate problem, whether it is a seasonal climate problem or a longer-term climate problem, we are not looking at the day-by-day, every realization of the state. We're looking at the statistics. We forecast the mean and the variance. We're asking, will next month, what is the probability that next month will be wetter than typical March? Okay, what is the probability that the next March will be colder than a typical March? So it is no longer an initial value problem, even though when we turn the crank, it looks like an initial value problem. Okay, so there, in the climate problem, then it becomes sort of, I'm saying sort of, we can argue the technical term, but it's a boundary value problem. So for climate prediction, what we need to know is for seasonal, for El Nino forecast, we need to know the sea surface temperature, the evolution of the sea surface temperature, that's the boundary condition changing, and so then we can use the changes in the boundary condition, slowly changing condition in the boundary condition, and then do the forecast, and then look at the statistics. Okay, so that's a difference in how we use the model. So obviously, since the 1950s, we've got better observations, faster computers, and improved physics. So modern climate models, we look at the whole problem in a, you get these web pictures. So typical pictures, we divide the world into a huge number of grids, and then we specify the solar irradiance at the top of the atmosphere. We have volcanic aerosols, greenhouse gas. We specify the composition of the atmosphere. That's the last decade. So we predict the state variables, temperature, pressure, wind, cloud cover, cloud height, 3D distribution of cloud cover, water vapor. Now we also predict liquid water in the atmosphere, soil moisture, et cetera, et cetera. So we predict the entire climate system at very high resolution. The last decade, we were going for finer than 1 degree latitude by 1 degree longitude resolution. And now the next generation, we're going for 25 kilometer resolution, horizontal resolution. Just so you have the number in your head, the surface area of the globe is 5 times 10 to the 14 meters squared. So you can count how many grid boxes. So then going with a high spatial resolution, we have high vertical resolution. So we've gone from, I don't know where we're now, 50, typically 50 layers in the lowest 10 or 15 kilometers, and then the ocean, 30 layers in the ocean, and then the soil, maybe 10 layers, maybe more. So with a high resolution, CFL comes back in, and Richardson, we need to pass information faster to the next guy, so we take very small time steps now, and so we calculate multiple experiments. So it's a humongous enterprise. When I did the calculation for the last IPCC, I did a very coarse resolution. I added CO2 into the climate model. So I put in vegetation, I watched the leaves grow, and they decompose, and the circulation, the carbon in the ocean, the phytoplankton, the whole bit. And it was the first calculation, and I did it at very coarse resolution, and I did a 1,000-year control run, and I was a nervous wreck. It took, I don't know how many months on the computer, and they were going to retire the computer, and I had to petition, and I said, I cannot move the code to a new computer. Please don't retire it until I'm done. But these are huge calculations. So the code at the time, at this time, I'm guessing, because I read the code, is somewhere between 500,000 to a million lines of physics. So it's not talking about all the housekeeping and stuff like that. So the variations on the theme, obviously I showed you the equations of how you implement it. The typical picture is a finite difference. You carve, divide into grids. So, but we've also done spectral versus finite difference. But then the spectral methods, obviously we have mountains. And so we have negative mountains, and we have the pressure Gibbs effect going around like that. So it's a headache. And so also variations, for example, in solving for horizontal wind, as I said, the circulation is quasi two-dimensional. So knowing the horizontal wind, you have to calculate the divergence, du dx, dv dy. Okay, so it's better to just rewrite your equations in the divergence and the vorticity. Okay, and then solve those directly rather than calculate the divergence, because that's where all the action is. a new approach is not to have a grid, a regular grid, because we have what we call the polar singularity. Okay, as the latitudes, as you go to the pole, the longitudes get smaller and smaller. So you have a singularity at the pole, and so there are many, many different ways of dealing with it, and this is an example of the geodesic grid that Dave Randall at Colorado State University has done. And so, the other thing is the vertical coordinate, and this has always been a problem, because when you have a mountain, your boundary condition, the wind is, okay, go like this, you're going to shoot, you know, unless you put in a boundary layer and slow the wind down, it's going to fly up. If the wind flies up like this, I'm going to have problems with my clouds. I'm going to have problems with everything. So historically, the first thing is we define a normalized pressure coordinate, sigma coordinate. So the surface pressure, so it's always 1 at the bottom and 0 at the top. But then then horizontal is not exactly horizontal, and so there's also all sorts of transformation that you have to do. For the ocean, it's particularly difficult because the density line, again, the ocean is at max, typically 4 kilometers thick. Okay, so when we have slight slopes in the density, so these are constant density lines and they slope, there's a lot of exchange along along a density line, but very little is stably stratified. Okay, so very little exchange across, diapignal exchange, very little. And if your coordinate is horizontal and can't deal with that, then you're going to have computational problems, and you have an artifact of very large diffusion in the vertical when you shouldn't have that. So there's a lot of problems of implementing these. But even at 25 kilometers, the important processes are smaller than that. Okay, so we can, at higher resolution, we can resolve topography, we can resolve the large-scale flow, but the large-scale flow is to a significant order driven by small-scale processes. Okay, so here we have the problem of resolving clouds and rain and aerosols, but also at high resolution, the way the old models are formulated is that when your grid is this big, okay, and the vertical is that big, you can assume turbulence is 2D, and when it comes back to, a cube, the same dimensions, then you have to look at the turbulence formulation totally. The spectrum is totally different. The energy cascade spectrum is totally different. What I want to go is here, so these are really important challenges. But what I want to spend my time on is the energy, what goes into the physics of the model. And this is a very brief summary of the Earth's energy balance. And I don't know if you've seen it, so I apologize if I'm repeating something you know. The sun is at 6,000 Kelvin. The Earth is at 300 Kelvin. So the emission spectrum of the sun peaks, as you know, in the visible part at 0.5 microns. The Earth's emission spectrum, the Earth is at 300 Kelvin, the Earth's emission spectrum peaks around 10 microns. So that it is very convenient for us to separate into solar and terrestrial radiation, or shortwave and long-wave radiation, or visible or infrared radiation. We're saying the same thing. So it's very convenient. The temperature allows us to separate the energy from the sun versus the energy from the Earth. So if we just put the energy of the sun here into 100 units, then there are aerosols and gases and in the atmosphere that absorb 20% of it. And then there are clouds. Okay, the clouds reflect sunlight, and then also at the surface, the albedo, the whiteness, the reflectivity of the surface, the reflectivity of the ocean is 6%, the reflectivity of snow and ice is 60 to 80%. Okay, forest is about 10 to 15, deserts about 20, 25%. So then altogether, they reflect about 30% of the energy. So of order 51% of the sun's energy is absorbed by the surface. So that in turn gives sigma T fourth. You know, this is a black body radiation. You have sigma T fourth. So there's long wave radiation. Some of the radiation in the window spectrum, until recently, there are no gases in the atmosphere that absorb in that part of the spectrum. So it is just going straight out to space. But there are there's CO2, water vapor, and methane, and nitrous oxide, and other greenhouse gases in the atmosphere. And so those go into excited states, okay, CO2 into excited states, and so they absorb the energy, and so then they radiate both up and down. Okay, and it is this downward energy which keeps our Earth warm. Without the greenhouse gases, without water vapor in the air, without CO2, the Earth would be 30 Kelvin colder than we are now. Okay, so when we look at climate change, then the climate change happens when there's changes in the incoming solar radiation, changes in the cloud, changes in the composition of the atmosphere, changes in the surface albedo, et cetera, et cetera, et cetera. So anything that we do that change any one of these arrows, everything changes. Okay, this is the whole thing about the climate system. So you're familiar with this figure, Mauna Loa Observatory. Dave Keeling went up to the observatory, and it's a really tough place to get to. I mean, it's a marvelous place to be once you're there, but it's a tough place to get to. I tried to go there, and I got lost in the lava, even though there was a line that says, follow the white line to the observatory. I got lost. So you can see very clearly the increase in CO2 in the atmosphere. The unit is parts per million by volume, i.e. if I grab 1 million molecules of air, I get 780,000 nitrogen, I get 210,000 oxygen, etc. So out of the 1 million molecules of air I have now, 390 molecules of CO2. So minute amount of CO2 in the atmosphere. So we have observations of these, and the ice core, from the ice core, the air bubbles trapped in the ice, we can analyze the composition, and we can back out the CO2. The important for my conversation is not the Vostok, and you've seen a lot of those graphs. The Australians have a very nice, we call a high deposition site. Okay, so a lot of snowfall so that you can see annual layers. So you can get really high resolution information out of the Australian from the high deposition sites. So we can have the CO2, the atmospheric composition, back to 1800. So once you have the atmospheric composition, you have to do what is called radiative forcing. You have to translate how much the energy absorbed. Okay, so you have to calculate the excited states, and this is an example from, this is Bill Collins gave me this figure. He's at LBL and at Berkeley. So now we define forcing. Okay, we have the background, we have the pre-industrial. Let's just use the pre-industrial as our control state, and so now we're perturbing it by increasing CO2 and other gases. Then what we can do here is the spectrum. Okay, so this is wavelength here. So, and this is the forcing. So you can say when CO2 goes from 180 to 270 parts per million, I get the blue line, so you can see where there is a lot of forcing. Okay, that means excited states. And so you can see as we slowly increase, these are stepping up. Okay, as we slowly increase, as the color goes from blue to yellow, these bands saturate. Okay, these bands saturate because you don't see the yellow anymore, but the wings come up. Okay, there is spreading. So there is, even though this has been talked about a lot, that oh, there's no greenhouse problem because the bands saturate. And that's true in this particular band, okay, but there's a lot of absorption in the wings. Okay, so what we have is a logarithmically increasing, is a monotonic increase. The forcing is a function of CO2, but it's increasing logarithmically. So you can take the observations of CO2, of increases of CO2, nitrous oxide, methane, et cetera, all the greenhouse gases, and you do the radiative transfer calculation for each one. You take into account the overlapping lines between all the various gases. You take into account where the gas is in the atmosphere, the vertical distribution and the pressure broadening and all that sort of stuff. Okay, so now you have the forcing. And so this is a summary, this is a summary of the forcing here. So you can see CO2, so these are positive forcing, and you can see here the spatial scales global, you know, whether we are confident scientific understanding or not. So since the 1750 to now, there's also change in surface albedo because the snow got darker because of all the soot, the dirty snow. But also there's conversion of forest to agriculture, and that changes the reflectivity. The surface got lighter. But there's two big blue blobs here. One is aerosols, and one is called direct effect, and the second is cloud albedo effect. Aerosols are suspended liquids and solids in the atmosphere. So you know when there's a hazy day, you know when you go to Beijing or Shanghai, it's high aerosol loading. But how much aerosols reflect, and you know they reflect sunlight, but how much aerosols reflect sunlight depend on the size of the aerosol. So you can just do a very simple calculation. Given a certain mass, smaller aerosols would have a larger surface area and therefore would be more reflective than larger aerosols. So there's a large uncertainty here because we didn't know the size, we didn't know about the aerosols in the 50s or the 40s, or, you know, the historical record. We do not have historical records of aerosols. And also we don't know the size distribution. But the other thing that happens with aerosols is that aerosols influence the cloud formation process. If you have gone through Gibbs free energy calculation, homogeneous nucleation is very difficult. So the presence of a condensation nucleus in the atmosphere, okay, helps the formation, the condensation. So what you see this is off the coast of California from MODIS satellite. You can see these very linear features, and so we have ship tracks. Okay, the ships emit gunk, okay, and the water condenses on the gunk. And so what we have are brighter clouds, and you can see very clearly the change in the cloud albedo. So the clouds get brighter because we have smaller particles in the atmosphere. This is a major uncertainty. You know, we don't know the aerosols, we don't know the size distribution, we don't know the hygroscopic properties, we don't know the chemical properties. You know, there's lots of things we don't know. But also, even when we see something like this in the models, which we can capture, we can try to capture all of these, we don't know about the lifetime of clouds. So if I have now smaller cloud drops, the clouds may hang out for a longer time, I don't know, okay? They may not. So there's all sorts of things that we are working on. So now I go to climate forcing. So summarizing those bars, then what we have here is the forcing. So this is the dashed line is the sum of all the red bars. Okay, the blue dashed line is aerosol, all the blue bars. Okay, and the filled in red here is the total. Okay, this is a Monte Carlo calculation. I won't go through all of that. What I want you to remember several numbers. The cumulative, the forcing, the greenhouse gases we have put into the atmosphere since the 1800s have given us a forcing of 3 watts per meter squared. Okay, that has been countered, we think, by the aerosols. And so that's minus 1.4, and the net so far that we have gotten from the forcing is 1.6 watts per meter squared. And I want you to remember those numbers. Okay, so now we have kicked the system. Okay, the next thing we do, you are engineers, you know the feedback. And for Earth, the feedback is water. So when we have an initial warming, then you know that we're melting ice, etc. So the melting, okay, we're darkening the surface, reducing the albedo from 60 to 80% to about 20 to 30%. So there's increased absorption of solar energy, so that accelerates the warming. And more warming, we have more evaporation from the ocean, and so that increases the water vapor in the atmosphere. Water vapor is a greenhouse gas. Okay, so that also enhances the warming. And so where the dial could be is increasing cloud cover, and cloud cover would reflect sunlight, okay? And if there's an increase in cloud cover, then there could be a decrease in the absorption of solar energy, and that would be the negative feedback. So the dial, a major dial of the climate system, is in water, okay? And the negative dial, the damping dial, is in the clouds, about which we can write poetry. So I'm going to go to this familiar figure. You guys have seen this figure before from Vostok. We from the ice, from the air bubble in the ice, and from the deuterium in the air bubble and the deuterium in the ice, we get the CO2 record and the temperature record, showing very clearly the 100,000 year, different cycles of the length of the Earth's orbit around the sun. So they look lockstep. What Jim Henson has done is to convert the CO2. Let me just back up. You can convert the CO2, like what I showed you, into a forcing, the methane into a watts per meter, forcing per meter squared. And so then what you have, the temperature is the response, and you can, we can estimate what the global mean temperature is from the Antarctic temperature. And so what you get, and so I won't go through the regression and etc., but you get a feedback factor from the ice core of about 3/4 of a degree Kelvin, 3/4 Kelvin per watt per meter squared forcing. Okay, this is derived, this is empirically derived from the ice core data. Okay, that over the last 400,000 years to lowest order, if we kick it, if the system changes by 1 watt, we get 0.75 Kelvin. Okay, so this is now, you come back, and so the way it is done is that you can now estimate something called climate sensitivity. Climate sensitivity, everyone uses, it's just partial derivatives. Okay, you have the total temperature, and you say, what is the total temperature as a function of water vapor, changes in water vapor, cloud cover, cloud height, et cetera, et cetera, et cetera. So then you can do this calculation, and when we did this is 1984. We did it on an Amdahl in the basement. So what you do, I mean, this is a really tedious calculation. You have to run the model, and you figure out what is the total change. You have to know what is the total change in water vapor, and then you plug it back into the model, okay, holding everything else constant. The only thing you change, and then you figure out what the forcing is. So what we have then from the calculation is that the forcing, the major feedback is in the water vapor increase. Okay, so this is the CO2 give. The major forcing is in the water vapor, and not only in the amount of water vapor, where the water vapor is. Water vapor in the upper atmosphere, upper troposphere, would trap the energy, and so there's less energy going out to space, so it would contribute to warming. And so there's change also, lapse rate in the temperature gradient, dTdz, and so that is a negative change, sorry. So albedo, we melt ice, okay, change vegetation, and so that would be a positive forcing. And cloud height, I'll come back to cloud height. So when we have higher clouds, okay, it's more energetic, warmer, there's more convection, there's more energetic, higher clouds, then the cloud top would radiate to space at a colder temperature. Okay, so there's less heat lost to space, therefore warming. So if we come back here, so the two things are the same. For 2 times CO2 forcing, you can calculate a forcing of 4 watt per meter squared using the feedback factor I just showed you. Then the climate sensitivity, okay, which is just defined, it's just a convenient term, is 3 Kelvin. Okay, so you get the idea of what we have to do. So now we come back to the greenhouse gases. Remember, I said, remember 3 numbers, okay, 2 numbers. One is if only greenhouse gases, we already have 3 watts per meter squared forcing since the 1800s. Okay, I apply this climate, the feedback factor, we have over 2 degree warming in the pipe. Okay, this is equilibrium. This is very serious stuff. Okay, when you ask me why we feel urgent, this is the reason. Okay, we have already committed to 2 Kelvin, okay, when the system comes to equilibrium. But when we added aerosols, aerosols counter some of the warming, some of the forcing, so only 1.6 watts per meter squared. So then we now, at equilibrium, if we keep aerosols, if we keep Beijing, if we keep, you know, all the cruddy atmosphere around, then we would have a lower temperature increase, about 1.2 Kelvin. So those are equilibrium calculations, you know, so you have infinite time for the system, but the ocean is stably stratified, okay? So then any heat, anything that we put in the ocean, it takes a long time to diffuse, okay? But when you warm the ocean, then there's more evaporation, there's more water vapor that contributes to more warming, that warms the ocean some more, et cetera, et cetera, et cetera. So that it's not just the thermal inertia, it's that feedback coupled with the thermal inertia of the ocean that gives us a time scale of at least 100 years. So what we have then is what we realize, the warming we have since the 1800s, it's about the last 2 years warmed a lot, so I'm trying to update my head, about 0.6 to 0.8, and don't quote me on that, I have to check. Okay, but what we have realized is less than what is in the pipeline. Okay, so we have pipeline because we haven't come into equilibrium yet. So that's basically, you know, all the pieces you need to know about climate warming, that there is the forcing, and then there's the feedback, and the feedback is the climate, the feedback is controlled by the water cycle. So when we look at all the different models, now, so this is IPCC, a lot of models, each dot is a model, but different, I just won't go through in the color, but this is the opposite. So this is, we plot things differently. So this is the same, okay? This is a 0.75 here. They just flipped it, it's the reciprocal here. So we're looking at the same thing. Okay, water vapor is a positive feedback. The largest feedback, positive feedback from all the models is in water vapor. Cloud, okay, I said, even though I said if I had increase in cloud cover, I would have a negative feedback. It turns out that, I mean, it's not, it turns out, you know from Clausius-Clapeyron, from the equation, from water, the phase diagram of water, that when it is warmer, the atmosphere can hold more vapor. Okay, it's basically 7% per Kelvin. So the atmosphere reservoir has increased with every increase in temperature, and so there's actually decrease in cloud cover when we, in all the model, I'm not saying in real life, in all the model calculations, we all have a decrease in cloud cover, we all have higher cloud cover, so we all have a positive feedback from clouds. And so albedo, obviously, we're melting snow and ice. Everyone has a positive feedback. We all have a change in the lapse rate in the same way. But anyway, so you can see that all of them together, we have a feedback. I mean, so we have a, in some general sense of agreement or disagreement, depending on your viewpoint, this, okay, the positive feedback. So the IPCC, you've seen this figure before, the observations, you know, if we run, let's start with this one, the black line is the observed temperature change, globally averaged, and the blue, the swarm of blue lines, this is the United Nations effort. Every model, contributing model gets a spot. Okay, so we do not throw out anything that is less sophisticated or less reliable. So the blue line is everybody's average, and so you can see that the observations, you know, when we include all the greenhouse forcing, then we have a better agreement with the observed. and I won't go into this, but what I want to go into is where is the action? Why is it so difficult? Imagine, again, this is the phase diagram for water, so this is temperature. Suppose you start here, okay, and you go to this position, from A to B, then you add more water vapor in the air, there's more long wave absorption, and so this is going to be a runaway greenhouse, okay, runaway warming. But if I go from here to C, then when I cross the line, then I have condensation. So before I cross the line, it's warming. If I cross the line and I get nice flat maritime stratus clouds that rain on us, then I have cooling. Okay, so half a degree of temperature, who cares about? Except when you have to change phase, and then it's a 0-1. Okay, and so how far, so this is the challenge, is how far am I lofting the clouds? I mean, the water vapor, where do they condense? And then when they condense, what kind of clouds they form? Okay, so that's one of the challenges, is how do we predict clouds? How do we write the rules for clouds? And so here you can see from satellite, from the observations, this is the short wave, this is a solar part of the spectrum, this is long wave in the infrared part of the spectrum. Bright clouds obviously reflect sunlight, and that's why you see it in the solar part of the spectrum. High clouds, as I said, less emission to space, and so they enhance warming. And then we have some low bright clouds, okay, that cool the surface. Okay, so low, so they reflect sunlight and they cool the surface. So precipitation. Society doesn't care about half a degree change in temperature, doesn't care about 1 degree change in temperature. We care about changes in precipitation, especially changes in precipitation extremes. So when I look at precipitation, I can go through, we went through, condensation, you cross the line. But when I think about modeling precipitation, it's the second derivative of temperature. First I have temperature, which is pressure, and then I have convergence, the wind. Okay, the wind is the pressure gradient force, so that's the first derivative of temperature. Then I have convergence to get the lofting, and so I'm looking at the second derivative of temperature, okay, to start. Okay, it's one thing to say temperature, second thing to say I can get the second derivative of temperature, and then to get it up to the right altitude and condense. So this is a figure from the IPCC report, so you can see the dotted areas are where we agree in the sign, not the magnitude, in the sign. So some obvious things, which is here, in the tropics it gets warmer, there's more evaporation, there's more precipitation. But here, where there are no dots, but it's showing drying, decrease in precipitation, we have the Hadley circulation in the atmosphere. The air rises at the equator and then sinks, okay, around 30 degrees north and south. That's the Hadley circulation. That's the location of the Sahara Desert and a lot of the deserts. Now, what we're saying is that the sinking branch of the Hadley circulation is moving. The Hadley cell is expanding. Okay, so it is the sinking branch is moving poleward towards us. Okay, so this is a reason for concern. And so yes, there is an agreement, because some of our models have a little bit of expansion, some other models have a lot of expansion, and so there's not agreement. At high latitudes, where the atmosphere holds so little vapor, so any addition of the vapor will come down as precipitation. So I want to come back, and I'll end very quickly. Here, when you look at the other figures accompanying this, is that we looked at precipitation, evaporation, obviously. When it's warmer, there's more evaporation. But look at this figure, soil moisture. This is the parameter important for the albedo. Darker, wetter soils are darker. Okay, this is important for all the ecosystem dynamics, obviously. It is important, for the boundary layer turbulence, how high the boundary layer is, and there are very few dots. Okay, this is one of the major challenges of the climate modeling, is how do we represent the water under our feet? We cannot, because what we have is very heterogeneous composition under our feet, and there's no motion that, anyway, so you get the idea. what I want to end with is several things. One is I asked the question, how can we predict the weather? Okay, so many of you know the equations. That's Ed Lorenz when we went hiking. Anyway, so you know the chaos equation. So chaos, the first chaos was you have a heated from the Rayleigh, so you have a fluid heated from below, and the Rayleigh number tells you that's the strength of the heating. The B is the parameter. The crucial parameter is the Prandtl number here, the ratio between diffusivity and viscosity. So when you heat from below, when you have enough heating to initiate convection, then the heating, the viscosity tells you how fast things would go around, and the diffusivity tells you how fast you're losing heat as you're moving around. So then if you rise somewhere, when you get to the other side, then you know whether you have the temperature gradient to allow you to fall, or the other guys will come out. Okay, so this is where so you can do, then this is just the x, the stream function. So you guys have played, everyone has played with that. But this is where I come back to the issue of why should we be able to predict the weather. So this is multiple, so I perturbed the simple equation. Multiple, I did 10, this is real 10 calculations, and you can see they sort of follow one another at the beginning, and then they diverged. Okay, so again, I remind you, weather is the event. Okay, whereas, and so in this case, it is unpredictable. Weather's not unpredictable after 5 time steps, whereas climate is the average of the weather. So when I take this and then I average, then we have the mean, and then we have the PDF. Okay, so here, even using the chaos model, and this is Lorenz. You know, the reason the 3 equations is to show that there's a limit to weather prediction. Okay, so now what we are using is to look at the climate in terms of the same equations and say we're looking at the statistic of the climate, and even with the chaos model, we can have a sense of predictability. So I'll finish very quickly. So you can see with very simple Lorenz 3, the chaos model, what I did was I ramped up the heating linearly. Okay, that's in the classic one, it's a constant. Now I ramped it up. And so here's the mean. So this is a mean climate, okay? So it is increasing. I just plotted x, which is the stream function, so it's going faster and faster. But this is the standard deviation, okay? And I look at that as the weather. Okay, so you can see the weather getting more violent. Okay, we're going to have extreme heat and extreme cold, extreme whatever weather. Okay, floods and droughts. Okay, so the variance is increasing in a very simple model, and this is also what we get in the big models. So I'll stop here and I'll just talk about observations, challenges. You know, observations, okay? So we're talking about multi-scale modeling. There are all sorts of things I have not had time to talk about. Data assimilation, you know, dynamical systems. There are a lot of things going on in here. I have been working on ecosystem models, putting ecosystem models into the climate model, and it's a big challenge. So what I have done, I'll just talk about something I'm doing now, because I went in a fit of arrogance, I went to my friends and I said, you guys are measuring the wrong things. So we have a new program where we go out in Northern California, and we have a site where we have instrumented, very small site, and we have instrumented the atmosphere. We drilled now about 15 wells all the way down, and we have put sap flow in the tree, so we know whether the tree is putting water up or down. You know, the roots are putting water down, and we have brought in neutron probes to get the profile of water. And so this is a new approach to trying to understand, you know, identifying what we don't know in the climate model, and trying to go out and look at the data, okay, and gather new data and figure out what to do about it. Okay, so I'll stop right there. This is another marvelous challenge for me, so I'll leave it up here. This is satellite image again. of open cell convection and closed cell convection. Sometimes when you fly, I flew back Saturday, and I said pancakes. Okay, so you know Bernard, Rayleigh Bernard convection. You see the hexagons. So sometimes we see pancakes, filled hexagons. Sometimes we see lacy, open. Okay, open cells. So it's the edges. So what we are now looking at is that, you know, if you just do convection, if you have plus delta T minus delta T, you get symmetric cells. But if you change that to a flux boundary condition, it makes a difference whether you're heating from below or cooling from the top. So heating from below, you have the lacy patterns. If you cool from the top, then you have closed patterns, okay? And so now with the new observations, I say, where do you think it is raining? Not in the pancakes, okay, at the corners. Okay, so now there's just new observations that's coming in that find that they can oscillate, and it's just marvelous. So this is one thing, you know, we're trying to write, they're beautiful pictures, but we're trying to write the equations, we're trying to understand the dynamics of what is going on with these cloud structure and what is the subgrid, you know, what is the level of detail we need to represent in the climate model. So I'll stop here. Thank you very much.